Problem 6, we have an ideal gas and we have a cycle. It means we start by the point A, by the state A, we go to the state B, B, C, C, A. First of all, so we can say here, initially we have state A, we go to state B. A, we have PA, PA, VA, and here we have PB, VB with an isothermal compression. So when we have a compression, in this case, isothermal, it means delta T equals to O. And when the volume decreases, in this case, we have a negative work done by the gas. So the work done during this process must be negative because we have a decreasing of volume. Okay, now we start from the point B to the point C. We go with a constant volume. So delta V equals to O, constant volume, so omega B C equals to O. Okay, and we have a reversible adiabatic relaxation. It means the volume increases from the point C to the point A. Adiabatic, it means Q or delta Q, we can say Q equals to O. Q CA equals to O. The volume increases, so omega CA must be positive. We have A, it's a constant. I give you A equals to 2 equals to VA divided by VB. So VA equals to 2 VB. Okay, so we can say VA equals to VB. And we have PA equals to 1. Part 1, I have to draw the Clapeyron diagram. It means we have to put X and Y, V, P in function of V. Okay, so here, you know, we can draw Y-axis. Here we have P and V. Let's say initially we have a point A at VA. We go to the point B by decreasing the volume where VA equals to 2 VB. Let's say here we have B. Okay, we can put it like this. Okay, here we have the point B, and the isothermal diagram path must be very slow. You cannot do like this. It's slow. The adiabatic process is very hard. We have a big slope. So here we go to the point B. You know, when we decrease the volume, we increase P in the same time, okay? We increase P. It must be like this. We arrive to the point B. And second, we go from the point B to the point C by a constant volume. Constant volume, it can be down or up. up or down. If we have heating, so P increases. If we have cooling, P decreases. Okay? If you come back to the problem here, we have reversible heating at constant volume BC. So we give a quantity of heat. In this case, we have heating. So in the case of a constant volume, when we increase the heat, in this case, P increases. Okay? You can, we have like this, we arrive to the point C. And finally, from C to A, we have an adiabatic process. You know, adiabatic, it's like the isothermal, but with a big slope. Oops. Let me. Okay. Like this. This is Q equals to O. Here, T is constant. T is constant. And here we have volume is constant. We can say delta V equals to O. And here we have delta T equals to O. And here we have VB, where VA equals to 2 VB. Okay, I don't respect the distance, just anyway, you know VA equals to 2 VB. This is part 1. Anyway, you know here, we come back. Part B, I have to find PB, PC, and TC, and I give you A. Okay, let me write here the given. I want to calculate PB, PC, and TC, and I give you PA, which is equal to 1 ATM, and we have A equals to 2, and we have TA, we can say we have TA equals to 300 Kelvin, and I give you gamma equals to 1.4. Okay, I want to calculate these parameters. Now let me find PB. You know, to find any parameter of B, you can take 2 points, AB or BC. Here we have the value of PA and TA, so we can take directly these 2 points, A and B. Here we have an isothermal process. In this case, you know PA VA equals to NR TA divided by PB VB equals to NR TB. We can eliminate the constant value TA equals to TB. We get finally PA VA equals to PB VB. Okay, I want to calculate PB. PB equals to PA VA PB PA VA divided by VB. You know VA divided by VB equals to 2. So, and PA equals to 1. So here we have 1 atmosphere. You have to put it in Pascal times 10 power 5 Pascal times 2. So we get here 2 times 10 power 5 Pascal. This is the value of PB. We can put it here directly, where PB equals to 2 times 10 5 Pascal. Okay? Part 2, I want to find PC. PC, we can take, for example, the point B and C. We have V constant. So P, so here we can take the point B and C. Divided by P. C VC equals to nRTC. We have a constant volume, N and R, so PB divided by PC equals to TB divided by TC. Here we don't have the value of TC and we don't have the value of PC. So we don't have PC and we don't have TC, so we cannot use this formula to calculate PC or TC because I need to calculate PC and TC. In this case, we have to use another formula. How? Anyway, you know TA equals to TB. We have the value of TB, but I don't have PC and TC. If I take the point C and A, maybe it's easy to calculate the value of PC. So I take the path CA and you know the relation T gamma P1 minus gamma of C equals to TA gamma P1 minus gamma of A. Here we have okay, here I can use also we don't have TP, and also we have, for example, TC VC gamma equals to TA VA gamma. You know VB equals to VC, the same. VB equals to VC. So we can say VA, we have A equals to VA divided by VC equals to 2. So we can calculate TC. TC equals to TA times VA divided by VC equals to 2 power gamma. Gamma equals to 1.4. We can find TC. So it will be 791.7 Kelvin. This is TC. Each time you finish, you write the answer in the table. 791.7 Kelvin. And you know TB equals to TA equals to 300. We can write here TB, we have its value. Okay, each time you find TC, you can apply this relation to find PC. So PC equals to TC PB divided by TB equals to TC times PB. We have PB equals to 2 times 10.5 Pascal divided by TB equals to 300. We get the value of PC equals to 5.2 times 10 power 5 Pascal. This is PC. So we can write here P of C 5.2 times 10.5 Pascal. This is the value of PC. Like this, we calculated PB, PC, and TC. Part C, if the system has 1 mole, so N equals to 1 mole, calculate the work exchanged during the omega AB and the corresponding exchanged heat. We have to find omega AB and QAB. Be careful, you have energy, work energy, we have internal energy, and you have heat energy. Here, I ask you to find omega and Q. Okay? Find omega AB and QAB. And I have N equals to 1 mole. 1 mole. Okay. In general, AB, it's a isothermal. You know, in the case of isothermal, omega equals to N R T ln, you know, ln V initial divided by V final. In this case, no, it's the opposite, equals to V final. Anyway, if you forget the value of omega, you can write here omega equals to the integral P dV between A and B. Now I talk about omega by the gas equals to N R T ln nRT dV divided by V between A and B, because P equals to nRT divided by V. We have N is constant, R and T is constant, and here we get ln V final VB minus VA. So we have VB divided by VA. This is the value of omega between A and B. You know, B is smaller than A, so ln VB divided by VA must be negative, and omega AB is negative. Omega AB is negative. So we can calculate, we have N, we have R, and we have T A equals to TB equals to 300 times ln VB divided by VA equals to half, okay? Equals to half. Here we have VA divided by VB equals to 2. So we calculate omega AB, which is equal to minus the answer will be minus 1725.9 joule. This is omega AB. We can write here omega AB equals to minus 1725.9 joule. QAB, you know, in the case of isothermal, delta E equals to O. So, which is equal to delta Q minus the omega. So, dQ equals to the omega. Okay, so dQ between A and B equals to minus 1725.9 joule. Okay. Anyway, this is part. We go back. We calculated the exchange of heat. Okay, part D. Calculate the heat exchange during BC. We have to find QBC, and we have to find, okay, I want QBC. QBC. You know, BC has a constant volume. So we can write QBC equals to NCV delta T directly. We have N. If you don't have N, you cannot solve it like this. So N equals to 1, CV equals to R divided by gamma minus 1 times delta T equals to TC minus TB. Okay, we calculated TC, I think. Okay, 791.7 minus TB equals to 300 equals to 8.31 divided by 1.4 minus 1, and we calculate the value. Okay, this is the answer of Q. In general, you know, QBC must be positive. Why? Because we have heating. At a constant volume, we have a heating process. So dQ or Q of BC equals to 10 to 5.06 joule. Okay, we go to the last part. Deduce without new calculation the work in AC. We have to find omega AC, and we use the change in the internal energy between A, B. Okay, so I want to find omega AC. Omega AC. Here, to calculate omega AC, you can say delta E of the cycle equals to O, which is equal to delta E A B plus delta E B C plus delta E C A. Okay, delta E A B equals to O. So here we have delta E B C plus delta E C A equals to delta E equals to delta Q B C plus delta omega BC plus delta Q CA plus delta, no, minus delta omega CA equals to O. You know QCA equals to O because it's adiabatic. So we can calculate omega CA or delta omega CA, which is equal to delta Q BC minus delta omega BC. We have, anyway, we can calculate delta Q BC. We have it here, okay, equals to 10,215.06 joule minus omega, delta omega BC, you know, equals to O because we have a constant volume, so equals to O. So in this case, delta omega CA equals to delta QBC. Okay. Anyway, it's very important problem just to understand the physical meaning and to practice about the first law of thermodynamics. Okay.